Okay, welcome everybody to Mechanistic Interpretability 1. Benjamin Gerraty, who's a PhD student with me at the University of Melbourne, is going to introduce this field. So go ahead, Ben, and welcome.
Awesome, thanks guys. Just checking you can hear me okay? One more time. Awesome. So yeah, like Dan said, I'm I guess I'm still a new PhD student, but that gets less true every time I say it. And I like to identify as that because it makes me feel a bit better about my current knowledge base. Anyway, so I'm going to be giving us a bit of a run through of a rough introduction to what Mech Interp is, and mostly talking about the toy models of superposition paper. If you're an expert in the field or you've read the paper recently, I'm not sure if you're going to get a lot more out of it than I'll present, but if it's been a while or you're not super confident, then hopefully this will be helpful. At least it'll be good to have it in your mind fresh for Friday when Dan talks about it in his SLT High lecture. Okay, so like I said, most of what I'm going to be speaking about is from the toy models paper. There's a few other references that I've got here. I'll just show them all now. You might notice later in the talk in the top right, I'll have these little codes to link to what reference I'm talking about. So if you want to go over these notes later, then you can use that. So like I said, mostly toy models. There'll be a little bit of the Distill and other Anthropic papers to introduce Mech Interp a bit more generally. And then we'll finish off with a little bit about the second toy models paper, just if we have time at the end. Okay, cool. So quick introduction of what mechanistic interpretability is. Basically, it's this image right here. You look at a network and then you try to interpret what it's doing, and then you create an explanation. End of talk. But no, basically what you do is you kind of stare at neural networks, looking at the weights and the neurons, and try to come up with a explanation, or like, I don't want to say a story, but you can sort of tell yourself something about what the network is doing, and then you hopefully will try it to check if your explanation makes sense. So the reason this is such a big problem is that we don't really know how these AI make decisions, which is not a great state of the art, considering how wildly spread use they are. Like I think GPT-4, I heard, was the best-selling product of all time. So that's certainly some inclination that
Fastest adopted.
Fastest adopted.
Oh,
okay. Yeah, it's definitely quite popular, to say the least. And yeah, this model, well, GPT-4 especially, is not incentivized to be interpretable by humans. So, like I said, mechanistic interpretability, quite a small field and a new field of people looking at these models and the weights of the neurons and trying to see if they can figure out and reverse engineer what's going on, similar to reverse engineering computer programs. Something that a lot of Mech Interp people mention quite a lot is this curse of dimensionality, which is the issue that these models are very, very high dimensional. I think GPT-3 is like 175 billion parameters. GPT-4 is probably a lot more than that. And so when you deal with these high dimensional spaces, understanding anything can be very hard. And that is why we are going to look at some toy models today with much lower, much more interpretable things. So to deal with not knowing what these networks are doing, the main objects of mechanistic interpretability are things called features and circuits. And I'm going to introduce these pretty briefly, mostly as motivation, so that we can sort of see why people care so much about this toy models of superposition by Allard et al. Paper. Okay, so let's say you've got a network and you want it to be interpretable, like you're assuming that it can be. What is something you would want the network to have? What is a feature, colloquially, of a network you would want it to be? This is what the idea of features are, is we want to be able to look at a network and see if we can say something about what a feature colloquially is about it. So the main idea here is that the neurons in a network are thought of to look at people think of the activation functions or the neurons to represent features. So some quick possible definitions. I think this is best learned by example, but a feature could be thought of some property of the input of the function, which a sufficiently large network would reliably dedicate a neuron to representing, meaning that you would have, say, if you had a network large enough, then if you had a feature of the input of the model, that if your network was large enough and had enough spare neurons, it would eventually dedicate one neuron to represent one feature. Other examples is as any input of the model. This one has the issue, I guess, of being thought of as a feature. A feature could be a feature of features, or like multiple features in one neuron is still technically a feature. We also want these to be interpretable by humans. I don't think we want this to be the only thing though, because we, if AlphaFold finds some new interesting feature of protein folding, we want that to be still declared a feature, even if we didn't find it and we don't really understand it yet. If this is a bit fuzzy, that's okay. I think looking at examples is the best way to define a feature. And if anyone in the audience or has an idea of a good way of defining a feature, like if they've figured it out, please send something in the chat. I'd love to hear how you think of the feature. I've had a lot of different opinions and I'm always keen to hear more. So the colloquial example that I think of in my head as like what a feature is say in an image classifier, if you look at a specific neuron, so here we've got in this neural network called Iceptron V1, this neuron on the left here is this is the input we're looking at, this weird dog mold thing that maximally activates that neuron, that makes it fire fully. And as you can see, it looks like it's a bunch of weird dog type shapes meshed together. And so you might think that this is what I'm going to call like a dog head detector. So when this neuron fires, it's because that it is seeing a dog head. Another example could be something like a curve detector. So these are some inputs that make some neurons fire in the same model that maximally activate the neurons. And we can see that these look like it's trying to detect curves. So that could be a feature that is detecting curves. Moving away from just image models, you could think of in like a transformer token-based AI. This one on the bottom left is what I'm going to call a base 64 detector. So this one activates strongly when it reads base 64 tokens, and then does not activate when it reads like words, which can also be thought of made up of these tokens. So if you look at the highlighted text, it activates strongly on stuff like URLs, where it's just got a bunch of string of base 64 characters. And then if you look at the logic weights next to it over here, you can see that it increases the weight on base 64 texts and then decreases it on just like actual words. And another one that I thought was kind of cool was a neuron that fires only when referring to a number of people. So it wouldn't just fire on numbers or just people, only when these two things are together. So this could be thought of a neuron that fires when referring to a number of people. Okay, so that's kind of what a feature is. We kind of think of it as like an interpretable object of the network. So how could we think about these networks using these features to give us the responses that we see it do so well? This is what we're going to call a circuit. So these are algorithms that it's like a subset of neurons or features and then links them together with certain weights and that reliably performs the same task, is how I think of what a circuit does. I'm not going to talk too much about circuits because that's mostly going to be for Rowan tomorrow in induction his paper. And again, a bit of a fuzzy definition, I think, less fuzzy than features. But some quick examples to motivate it. You could imagine circuits that combine previous features of different orientated dogs and then create an orientation invariant dog head like here. And the canonical example that people always show is this car detector feature that is been created from these previous features of like car window, car body, car wheel features. And then these, in some sense, seem to assemble into a car detector feature. So these are all supposed to be just meant to be motivational examples so far. Okay. So the other thing about mechanistic interpretability is that we want these features and circuits. We want to know, do these appear across models, or are they just all going to be purely an artifact of every single specific model we look at? So there's different ways you could frame this hypothesis. There's weak universality, where there's a handful of algorithms or circuits that will, and features that will appear across different models and scales. There's the strong universality, where all models perform the same circuits regardless of model type or scale. This one I think is, at least in my opinion, probably less likely to be correct. And then there's the one that I think is probably the most likely to be correct, is the universality of principles, that techniques that models learn would work across a wide range of models, even if the circuits and features are not necessarily exactly the same. So an example of this would be in this image classifiers I showed you earlier. We see that different models all seem to generate their own kind of curve detectors. And then another feature that these models create, as ones I didn't mention earlier, is a high-low frequency detector. So this is a feature that the authors did not expect to see, but that the model seemed to create these features that will detect high and low frequencies in images. And again, these seem to appear across multiple different models. Are there any questions so far on all of that? None of that is going to be super important for the paper, but it's, I think, good motivation for why people care about the paper.
Everybody looks pleased and content.
Wow, that's good. So why do we use these ideas? That should not have appeared first. But the idea that you can reverse engineer a neural network is similar, as people might have read Chris Olar's essay about how it could be analogous to reverse engineering a computer program. So a way that you could check if these, say, because the thing is, you could look at, these nice story of like, you got these features and these circuits, and then I've got an explanation and I think it's right. But before you go and like claim that's correct, you have to sort of check a bit that it works. So you could then find the weights and manually implement a new network and check if this like sort of handcrafted network still does what you think it should do. And so one interesting thing I've seen is recently is DeepMind is creating this thing called Tracer, which is like a sort of like a sanity check on where you have a neural network, you interpret it, and then you sort of check, is your explanation correct? And then Tracer will sort of create like a decoder only transformer to implement your explanation and check that it works. Okay, so now we come to the main topic of today. So this all sounds great. Like we've got networks, they've got features, they form circuits. It seems to appear across multiple models. What's the problem? Why is this so hard? So the issue is that most of the time, neurons and networks do not form these nice interpretable features. And often, not every neuron will align with a different given feature. Like I showed you before, we had that dog head. So that's like a feature of dog head aligns with that neuron that I showed you. Similarly, like the feature car body aligns with the car I showed you. Most neurons you see are actually what we're going to call polysemantic or in superposition, meaning that it's doing multiple things at once. It's trying to represent multiple features. And even if it's not doing that, say you've got, for example, you have your car body, windows, wheels, that combines to form your nice car total, that's good. But it still has to get that information if that neuron fires to the end of the network. So the car feature here is then spread across many other polysemantic neurons, which you can see there's like the middle one on the far right looks a bit more like a dog, but it's still got to carry that car information through. So that's mostly why they do it, is they need to get the information to the end of the network. But there's also the fact that if the features we see are sparse, meaning they don't occur very often, then the model is more happy to take the risk of shoving multiple features into one neuron, because it's like, well, I've got space for it. Why would I dedicate this whole neuron to just doing one thing? If that one thing doesn't occur very often, I might as well accept the tiniest decrease in maybe some decrease in performance to shove multiple things into that and let it do multiple jobs. So you can imagine like most neurons have like maybe a full-time job either doing one feature, like the car body detector, or a lot of neurons have most have a part-time job, at least carrying previous neurons information through, and maybe they're trying to detect 2 or 3 features at least, etc. So a helpful way I think of thinking about this is that every neuron has a certain capacity. So say here we've got the top 2 neurons, say if the capacity is between 0 and 1. These top 2 are what we're going to call purely representing features, in the sense that they go through the activation function sigma, and they are monosomatic, meaning that they just fully map the same features across. Then you can have features that are impurely represented that then combine to form what we're calling polysemantic features. And then sometimes you'll see neurons that don't activate at all, depending on the data we're looking at. So real quick, before we motivate why we want to solve this problem, can we just get rid of it? Can we just stop neurons doing it? That would be a lot easier. So clearly it's very challenging for interpreting stuff if what we're looking at is doing 25 different things at once. So the issue is if you got some features that never get a dedicated neuron and they're always in superposition, it's very hard to know if they're there, like ever. And so that's not great for alignment or AI safety. You know, if you want to declare an AI safe, we want to be able to see everything about it. And if it's hiding, it's like kill all humans functions in superposition, we'd like to be able to see that. So a idea that Anthropic had was to try to force more features to be interpretable. So force more features to align with dedicated neurons. And the way they did this was they took a 1-layer decoder transformer and they just replaced the activation function with what I'm going to call a SOLU, which is just, if you take the input X, you then multiply it by the softmax of X. And what they found is this did make features more interpretable. The problem was that it increased the loss by like 50%. But then they added a second layer normalization after the SOLU. So I guess what they really did was they replaced the ReLU or the GELU with a layer normalization of the SOLU. And after this, the performance was the same, and they still kept more interpretable features. I think, like, you know, as you can see here, around 60% were considered interpretable. And defining interpretable is they showed someone a picture of like what a neuron was doing. So for example, that base 64 token thing, and they gave the person 1 to 2 minutes to stare at it and try to guess what the feature was. And they found that using this function, around 60% was better than the 25 to 30% it had before. The problem was, in a sense, like by stretching out to make these more features interpretable, they were squishing the ones that they didn't see into more superposition. And by adding the second layer normalization at the end, they think what's really going on is that the model's just sort of using that to sneak in through more features in superposition than before. So in a sense, there's like no free lunch. Like you shine a light on these features and you see them, and then the ones that you can't see just sort of like shrivel away into the dark and hide. So it seems like superposition is here to stay. It seems like it's a very clever thing that models do. It's very well, good. That's like why the models are so good, because they get very low loss, and GPT-4 is amazing. So it seems like if we want to understand models, we probably need to look at this superposition thing. So what motivated Anthropic's paper was this thing called the superposition hypothesis. I'm not sure if I think this is true. I don't even know if they think it's true, but I think it's worth showing at least. So the idea is that you've got some observed model, and maybe there exists some hypothetical, much larger model where every single feature is given a dedicated dimension, or meaning that every single feature has its own neuron, and it's perfectly interpretable. It might not have the same loss. It might not be as good, but it's interpretable. And then this hypothetical model is then projected down into superposition of what we see. This could also, like the universality hypothesis, depending on how you frame it, could also not be true. In any case, it seems that superposition is definitely something worth talking about. Okay, so now instead of thinking of features as images and tokens, I want you to think about features being directions in activation space. So meaning in the local basis of the neurons. So the intuition behind doing this is, well, we could think of if we map neurons into high dimensional space. Well, one reason is that models are very good at doing linear algebra and especially transformers. There's some motivation here, again, take this loosely, that if you embed your tokens into a vector space, you can maybe sort of do some algebra where if you like start with king and go backwards from man, and then add the token woman, you get it queen. And yeah, so for the sake of this talk and for this paper, we're going to think of features as being inputs in an n-dimensional vector. So if we have x from x1 up to xn in R to the n, each xi is a feature. So this is feature x1, feature x2, and each will be associated with a real number. And then we can embed this feature into a vector space by multiplying it by some matrix W. So if we have, for example, if we plot two features into R2, these will look like just two directions in space. So this is feature X1, where W1 is the local coordinates of the W matrix that we embed it with. And then I'm also later in this talk going to often refer to WI or W1, W2, W3 as the columns of the matrix W. Just so if you ever see W sub I, I mean the columns of W, unless otherwise explicitly stated. And then there'll be some basis here. Any questions so far? Is this idea comfortable with everyone? I see a thumb, that's good. Okay. So before in that little bottom right image, I drew a dashed line with some basis. Do we care about it? Yes, because if we're embedding features in directions, it's natural to ask which directions. Does the basis matter? Does it not? Why? So this idea of superposition occurs when we have non-zero dot products with these different features. So before I just showed two features in two dimensions, they were orthogonal. They would have a zero dot product. So you could not make one as a linear combination of the other. And so those are both very much cleanly represented in their own local subspace. So it only makes sense to think of a neuron as interpretable when it has something I'm going to call a privileged basis. And so to show you what this means is, so if you visualize your local space as a set at the end of a layer, you've got the neurons. If a feature fully aligns with the basis dimensions, then you can, see it. And that's what you're seeing when you look at the neuron's activation. So for example, in the tokens and the image classifier, these had privileged basis. The ones we're going to look at today will not have a privileged basis. So we can see on the left-hand side here, and what I drew before, the features could just be mapped into any direction in space. So polysemanticity, when you see these features being combined together in one neuron, is when you see on the bottom left here, that this is what we look at when we see the neuron, is this basis. We look at the basis inputs, and you can see that these combine to form some non-zero dot products across here. And then if we then try to cram in more features that we have dimensions, then, so here we have three features trying to be pushed into a two-dimensional space. We can see that they can't align with the basis dimensions because there's too many of them. And then polysemanticity is inevitable. So the way that the toy model we're going to look at today is going to be trying to take that vector of n features, and we're going to try cram it into an m-dimensional subspace where m is smaller. So this leads us into the toy models of superposition paper. I might just refer to the toy models paper from now on. I'll try not to, but that will probably end up happening. So like I said before, if we have more features and dimensions, then the model will have to use polysymmetricity to represent that. It'll have to use superposition. So the context is going to be, we're going to have n features in an r to the n vector into an m dimensional space where m is going to be smaller than n. So the map that we're going to, so now before we embedded the n features into a n by n matrix W, now W is going to be a rectangular matrix. It'll be m by n. So when taking n features into m space, if I multiply by W, it'll make it smaller. The features we're going to take are going to be real numbers between 0 and 1. So each feature xi will be sampled from the uniform distribution between 0 and 1 for the rest of this talk. And the model we're going to use to sort of assess how well it's done. Let's see a question in the chat. Does privilege basis have a formal definition? To my knowledge, I think it's just when the features align with the neurons. So I think that's my interpretation of what the privilege basis. I don't know, but I don't know if anything really has a formal definition in this. So yeah, I hope that answers your question. So this is an image of the model we have. So we have this X features, N features, sorry. Then we activate, so W is like a full feed, full forward layer. This then connects to the M dimensions in the middle, and then we act on it with W transpose to bring it back up to X to the N. And then we add a bias on the end, and then we take a value, and this will give us this picture on the bottom right. It's worth mentioning in this model that there is no privilege basis, meaning that the basis dimensions don't really matter because, whoops. Sorry about that. Because you can see we can jam in an orthogonal matrix into the network. So if you look at this WTW here, if you replace W with an orthogonal matrix O times W, then you're going to get W, OT, OW. The OTW will be the identity matrix due to the orthogonality matrix. And so you can rotate your features in this W dimensional space and it won't change anything. Okay, so now to analyze this.
Something to add is that a place you don't have a privileged basis, for example, is in the residual stream of a transformer, because there,
yes.
I mean, yeah, ReLUs often induce a privileged basis, but in the residual stream, you can rotate the embedding matrix, and as long as you perform the opposite transformation before each attention head, and before the unembedding.
Yeah, thanks, Jesse. Yes, that's an example here I didn't mention, sorry. It's a good pickup. Okay, so to see what happens here, we're going to look at some features or some like hyperparameters to play around with to see how well this model does at taking these n features, collapsing them down into m dimensional space, and then trying to recover them at the end. So we're going to look at two parameters today called sparsity and importance. So sparsity is just how sparse your n dimensional vector is. So we're going to say that each vector, so each feature in the vector xi will be 0 with probability s. And if that's not the case, then with probability 1 minus s, it's just going to be sampled from the uniform distribution as before. So we're going to call s the sparsity. So if s gets higher, then more features can be set to 0. And if s is low, or if s is 0, then no features will be set to 0, but you might still sample 0 occasionally, I guess, from the uniform distribution. And then along with the sparsity, each feature is going to be given something called its importance, where more important features, meaning if the xi's feature importance ii is larger, the loss will be incentivized to map to recover that feature particular because it will lower the loss, which we'll see in a second. So yeah, if you've got a sparse vector, most of them are zeros. Typically, we're going to think of the importance as decaying exponentially. So I think in a lot of these plots, they give the importance for feature xi is ii, which is 0.7 to the I. I think this is just like the order of features doesn't really matter. They're just assuming that the first one is most important, but this is just an arbitrary choice to make it easy to plot. Okay, so the loss we want to minimize, so I'm calling here K of W, is going to be, so if you look in the inside here, we have, this is the input feature, and then this is the model. So we want to see how well this model does at recovering the X vector. So that's the difference here. This I is a matrix. So if you look at it entry-wise, it multiplies each feature by II. And so if I is high, then to make this difference, you want the model be more incentivized to remap that particular feature because it will lower the loss more. And then we just do a mean squared error loss, and then we sum or integrate over every single feature. And then this object here, Q of S, is basically just this binomial distribution of which features are getting set to 0 in this certain case. So here T is a subset of 1 to the n, sorry.
You've written equal to, but it's subset of, right?
Yes, sorry. Yeah. Sorry, T is a subset of 1 to the n because T can be any size. Yeah, good point. So I think, so a picture that I find helpful for this Q of X S thing is if you look on the right-hand side here. So if we have 3 features, then you've got probability S cubed that all 3 are 0. If only 1 is non-zero, then the probability is 1 minus S squared. So that's, then you got 3 of those. So they could be this axis, or this axis. And then these sides of the cubes will be only when, so this side, and this side will have probability 1 minus S squared times S. And then if it's anywhere outside in like the 3D box, when all 3 are non-zero, that's going to have probability 1 minus S cubed. Okay, any questions about the loss, importance, or sparsity before I continue? Okay, cool. All right, let's look at our first example. So if we try to embed 5 features into 2 dimensions, so this is the picture that I think of. So you got 5 inputs, X in R to the 5. You've got this W that maps you into a 2-dimensional space. So we can plot it in a 2D graph, which will be nice. And then we can try recover it with this W transpose. And again, for this context, Xi will have importance 0.7 to the I. So what we see is as the sparsity increases, the model tries to embed more and more dimensions. So if we start here, so each feature is labeled from most important to least important, with more important means more yellow, least important means more green. So what happens if there's 0% sparsity? So that means this is a very dense vector. Like there's hardly ever any zeros here. It's mostly, none are ever set to 0, except unless you like sample close to it. And then the model just orthogonally maps the most 2 important features. So it embeds only 2 features, the most important, the second most important, and it does so orthogonally because it needs to be able to grab back the important ones. And it just is happy to ignore the least important because it's not worth it from the point of view of the loss. Once the sparsity gets quite high, around 80%, it then tries to embed 4 features. So then there'll be some risk of, it still embeds the most 2 important orthogonally, and then it's happy to put the other 2 into the same local subspace of this line and this line. There will be some risk if, these 2 appear in the same vector, but it's happy to pay that risk because they're sparse. And then again, as you increase the sparsity even more, it tries to shove even more as like a pentagon. But as you can see now, every single feature has a non-zero dot product with every other feature.
Can I ask a question, Ben?
Yep.
The sparsity values there, are they theoretical or observed? Like in the paper, do they sort of show that you should expect the antipodal pairs at 80% sparsity, or are they
observed?
using
observed
observations experimentally?
Yep. There's that's a good question. No, it's experimental. I think every result I will show here is experimental.
Cool.
I got a question. Oh, Dan answered it, but yeah, the rotational symmetry is again on the features, not on the coordinates of the hidden space. That's right. So you can rotate in the hidden space, and it won't affect that. Okay. So, this is a bit of there's gonna be a lot of plots, which is gonna look like a lot when I first show it. So I'm gonna try to walk you through it a bit more closely. So let's look at the bottom left here. So we're gonna have 20 features now being shoved into a 5-dimensional space. I won't show this space for obvious reasons because it can't be shown. And then again, the importance is going to decay exponentially as 0.1 to the I. These are the matrix WTW. So as you can see here, when S is 0, often the paper shows the sparsity as 1 minus S. I'm not sure why. I think it's just a quirk they've done. So when S is 0, so when the sparsity is, again, very dense, the model will just embed the 5 most important features and then ignore the rest. And it will just, so then when you take WTW, you just recover the identity for the first 5 features. And then as you see, as you increase the sparsity, so here S is 0.7, once it gets very, very small, the model embeds more and more features. So we can see here is the norm of WI. So it's we got the matrix W, each column is WI. As the norm gets larger, so basically if it's close to 1, it will have embedded that feature because it's trying to recover a number between 0 and 1. And as we can see here, we've got a color code for how large the dot products are between the different features. So we can see here, these features are all orthogonal in the 5-dimensional space. And then as we increase, we embed way more features, and the dot products between them get more and more non-zero. Okay. So quick tangent away from the toy models paper. So coming back to the idea before we had of the capacity of neurons, we had this picture where I showed, imagine you have each neuron has capacity within 0 and 1, and some are being combined into superposition. Then as we just saw before, the way that you would expect if you had diminishing returns on embedding these features is they'll be allocated where you embed fully the first as many as you can, and then it will decay off, which is what we just saw before in the previous thing here. As we see here, we embed as many as we can, and then it decays, except for this one, but it mostly just decays off. And the reason I want to show this is because you could imagine there's different ways where, depending on the network, giving more capacity to one feature could have better returns. So if you have a loss for a feature for a neuron, Li, and it could have a capacity from 0 to 1, then taking the negative derivative of that, we can see if we embed more capacity into this neuron, the loss will decrease. Same with B. So in A and B, you get more, you're more incentivized to allow more capacity to a feature the more that you give it, because its derivative is increasing. And then in C, you just get, no matter how much you allocate a feature to a neuron, the returns are constant in terms of the loss. And then typically what we've been seeing in the toy models paper, and what we'll continue to see for the rest of this toy model, is the context of D, E, and F, where there's diminishing returns the more you allocate capacity to a certain feature. Okay, that's just a quick aside. Now back to the toy models. So we're going to see that if you look at this very low dimensional example of trying to shove 2 features into 1 dimension, so you've got like just a straight line, and then you're trying to embed 2 vectors into this 1D space. We're actually going to see a phase transition in whether it decides to, like a discontinuous decision, whether it decides to embed the feature or not. So here the feature vector is just 2 entries, and the matrix W is just going to be a 1x2 matrix. We're going to give the first feature importance 1, and we're going to let the feature of the second vary with importance I. So I will go from 0.1 all the way up to 10. So it'll either be 1/10 of the first one all the way up to 10 times it. So there's only 3 cases we have. So I think showing these pictures might be helpful. So the first case is if x2 has very low importance, say close to 0, then we will embed the first feature as just a vector w1 along the real line and ignore the second one. If the second feature has importance like 10 or 100, and it's very important, then the model will just embed the second feature and ignore the first one. And then if the importance is, say, equal, then the model will actually try to embed both. We can see here it's crammed 2 features into a one-dimensional space. And so this is an image from the Anthropic toy models paper, where they show, again, for that case, we've got 2 features in 1 dimension. So we can see in this gray region, we're ignoring the extra feature. This is when we have very low sparsity, it ignores the extra feature. And when the relative, so if it's low sparsity and the second feature is not as important, it will just ignore it. Funnily enough, even if the importance is very low, if the second feature is if the sparsity is very, very high, it will still try to embed that feature. It's worth noticing the log graph here. So it's 1, 0.1, 0.01. So only when the sparsity is very high will it actually do this. And then if the importance of the second feature is very, very large, it will just ignore the first feature, just forget about it, and just only embed the second feature with its own dedicated dimension. And as you can see here, this is all the different cases we have here. So it either embeds the first feature 1, 0 and ignores the second one, or it embeds the second one, ignores the first, or it puts it into an antipodal pair, as I drew in the 3 cases. Okay, so we're seeing that if we have more sparsity, then we embed more features. Now we can see that these actually seem to organize themselves into more geometric structures. So we've seen so far the pentagon in the first graph I showed, and we've seen the diagon in the one I just showed, just like an antipodal pair. It's worth noting that all these nice shapes is probably due to that we're going to see in a second, is due to the toy model we're investigating. But as we see these toy models are pretty much gold for analyzing SLT toolings. Okay, so how could we count how many features a model has learned? So a natural idea is look at the Frobenius norm, because this is a sum of the columns. And remember, we're associating each column WI with the number of features. And so if the Frobenius norm squared is what we're going to look at here. So, okay, so yeah, again, a feature will be learned if the norm squared is close to 1, and a feature will be not learned if it is close to 0. We'll see some questions in the chat.
I think it's
Okay.
okay.
It's okay. Yep. Daniel's handled it. Okay, so we're now going to think about this quantity D star as dimensions per feature. So if we're embedding n features into an m dimensional space, we would expect how many dimensions we've embedded per feature to be just the ratio of the dimension we're embedding into m divided by the number of features, which we're going to think of as the sum of the columns, or the Frobenius norm squared. And what we see is, if we just have to plot this quantity, is that when the sparsity is very, very low, we embed just as many features as we have dimensions. So m on the Frobenius norm is 1, meaning that we just embed m features pretty much. As the sparsity increases, we see that it drops off. But what's funny is that it seems to flatten out at this 1/2 point, which that we're calling the sticky points at 1 and at 1/2, meaning that when we get sticky at embedding as many features as we have dimensions, and then we get sticky again for a while for a lot of sparsity values, when we embed twice as many features as we have dimensions. And then again, we trail off as we try to embed more and more features as the sparsity increases. Okay, what if we wanted to think about a particular feature, xi, and look at that feature's dimensionality? Or how do we, if we think about like one feature, what if I wanted to know how many other features this one feature has a non-zero dot product with? So we're going to call this quantity dimensionality. So we're going to say a feature xi has dimensionality di. And so the way to interpret this formula is to think of the wi squared as how embedded that feature is. So again, if that's 1, it's embedded. If it's 0, it's not. And then the bottom is going to be thought of, yes, it's embedded, but how much of that embedding is got a non-zero dot product or combined from other features. So then we can sum over all features and take their dot product squared. And this is what we're going to think of the dimensionality of a feature. I think seeing some pictures might help motivate why we care about this quantity. So for 2 features in 1 dimension, we can see that if we compute this, we have a diagon. So we've got, 1 at the value 1, 1 at -1. The dimensionality is going to be 1 on 2. So we're embedding, think of this as embedding 2 features into 1 dimension. I'm going to color the diagons yellow, and we'll see why in a second. Some more quick examples. If we try to embed 3 features into 2 dimensions, then the dimensionality is going to end up being, with this quantity, 2/3. So if we compute the dot products between any one feature, they're all going to have the same dimensionality, by the way. So D1, D2, and D3 are all going to be 2/3. And then if we have 4 features into 3 dimensions, it's going to form this tetrahedron shape. And I'm going to color tetrahedrons blue and the triangles green. Also, you might notice that I've sort of traced out the shapes with these gray lines. So I want you to think of these gray lines as being, we'll see later in the next pictures that we're going to think of these gray lines as sort of being measuring how strong the dot product is between features. Okay, so now we can think about, what if we had like a lot of features, like 400 features, and we wanted to shove it into a 30-dimensional space. So this is what the plot looks like if you do that. If you take 400 features and you try to shove them into a 30-dimensional space, you're going to have where all the features are either not embedded, so the norm dimensionality is close. This is dimensionality on the x-axis, and this is the sparsity. So dimensionality on the y-axis, and this is sparsity on the x-axis. We're going to either not embed them, or they seem to localize at very certain dimensionality points. So we see that a half is one of the sticky regions that we saw before. So it seems that the model likes to keep these features at a half for a while, and then dimensionality will sort of trail off the longer we go on. All right, so now we've seen all that before. Hopefully when you see this graph now, it won't be too much of a shock. So everything we just talked about is now being combined into this one quite beautiful picture, actually. So let's take it slow. All right, so again, x-axis is how dense or sparse the region is. Y-axis is the dimensionality. Then they've also plotted in the gray in the background, the dimensions per feature, D star that we mentioned earlier. And so we see here, this is the sticky region, and then this is as it trails off. And then like the graph we just saw before, sorry, one sec. Why does the formula use inner products from the probability of? So we're always looking at the W dimensional space being small. So you wouldn't embed 2 features to R2. You'd embed more than 2 features into R2. So yeah, you would get, if you were embedding like n features into n dimensions, you would just get non-zero, or dimensionality always be 1, which is this like which would be this like dedicated dimension up here. Hope that makes sense. Okay, so, sorry.
Go on.
So we have here the dimensionality gets sticky at, well, seems to localize at 3 over 4, which corresponds to the tetrahedrons that I drew for you earlier in blue. And so these pictures up here, you can think of there being some like high 400 dimensional space. And then we're doing some PCA type, I think it's actually MDS projection or like principal component analysis to represent these as 2D space. And so each node will correspond to a feature like I drew before, and the edge weights are going to be the absolute value of the dot products. So you see in these connections here that features are going to be connected if they have non-zero dot products, and they're going to be orthogonal if they're disconnected. So you can think of this as some space where you've got some high dimensional space and then some local three-dimensional space that's orthogonal to everything else. There's this tetrahedron sitting there. And then this happens like 7 times in this example. And then the sparsity increases a bit. And then instead of forming these tetrahedrons seem to snap into different shapes. Now it makes triangles, the green ones I drew earlier, and digons. And then the sticky region is for a lot of values of sparsity. It will get stuck at this digon pair of embedding lots of just like a lot of one-dimensional subspaces up in your high dimensional space, just shoving 2 features into 1 dimension. And then as you see here, we then get some pentagons, like we mentioned before. We have 5 features in 2 dimensions, some square antiprisms where you have 8 features in 3 dimensions. And then as we just as the sparsity gets higher and higher and higher, the model just basically tries to embed everything. Just everything's like got non-zero dot products, and it's all just becomes this like big bagel soup of everything is just connected to everything. And then down here, we have the features that are not learned, and up here, the dedicated dimensions at the stop. So as we see, as the sparsity increases, we see a sort of phase change in which dimensionality or which like shapes the model likes to snap into. And we'll see, I'll talk a bit more about this in the second week about what's going on
Maybe
here.
you've said it already, but just to clarify that when you say it finds a pentagon, it means that at the end of training, so for each fixed sparsity, you run SGD for some amount of time, and then we're looking at the result. So SGD time is not on this picture. The x-axis is sparsity. No. You see the results at the end of training.
Yeah, I'll show some examples through training in a minute, but yeah, these are all pre-trained.
Sorry, can I ask a question, Ben?
Yep.
How do you understand or think about the sparsity values where you get, for example, the triangle and the digon at the same time? That's kind of interesting that like there's, I don't know, a precise enough sparsity value where you are actually seeing both.
Both, yeah. That's a good question. So I probably should have mentioned earlier as well that this is the constant importance case. So every single feature is equally important here. These are no longer decaying in importance. I'm so sorry. I should have mentioned that for this plot. To answer your question, I think, so because of the constant importance, I think it does not matter which features are in the triangles or which features are in the digons. I just think that's all going to be completely random since it's constant importance. As to why we go through this triangle phase, my guess is that this digon phase is quite stable, and maybe in transitioning from these tetrahedrons to get to this triangle spot, maybe like one feature leaves the tetrahedron and then that sort of snaps into a triangle, and then that one other feature joins with another feature to make a digon, or it just gets dropped off. You're
telling a story that has time in it from training. No.
Yeah, sorry.
It's just a picture. It's coexistence of the 2 phases. There's a digon phase and a triangle phase, and they coexist at that level of sparsity.
Do they, is there any talk in the paper or like in any of your results that show like that they coexist with the same posterior density, like same number of dots in each?
We don't understand the mid sparsity regime. So here you're looking at a graph of phase transitions induced by the truth, changes in the truth, the sparsity. We don't understand that. What we understand pretty well is the high sparsity limit. So there are phases and phase transitions there, but not induced by sparsity, induced by N. So that's what I'll speak about on Friday. It's an open problem, at least as far as I know, to understand what is in this picture, because that's talking about phase transitions in sparsity. That's actually much harder. That's a pretty hard problem, I think. In the high sparsity limit, it's pretty easy.
Cool.
Yeah, that's sorry, I kind of like, sorry, you go.
Just to clarify one other thing as well, in each, at each sparsity level, so like each column on this graph, are there 400 dots in each of those, and they just become extremely tightly clumped as the sparsity increases?
So there's 400 dots total, but not all of them are being seen, because you can see at the bottom here, the ones that are close to like at 0 are not being shown on the embedded graphs. So the ones we see are the embedded features. So the ones that have a non-zero dimensionality, and then it's not showing the ones that have, not the ones down here that are not learned. So no, like over here, it'd probably be the closest to 400, but even then it wouldn't be 400. Because you can still see there's some down here.
Yeah, so there's like a few hundred that are all being clumped up in that 0 feature row.
Yeah, exactly. Yeah, exactly. Yep.
Cool.
Awesome. And yeah, thanks for catching that down. That's definitely not correct what I said before. So this is basically the same plot as what we just looked at. This is one that I made myself, trying to understand how they got those pretty pictures before. So this might make it easier if you understand, or harder. But these are plots that I made where sorry, what was that?
You might be in Australia where modesty is prized. The talk is like logistically in America where modesty is not.
Okay. Sorry, I'm very proud of this. It's very impressive. So this is actually using, so what they use is not PCA, this is using actual PCA. So here, at least to me, the directions make more sense. So if you look at, so I've tried to color them the same way the paper did. So you see here, there's some triangles here. They're harder to see because, you know, there's some like, all the values of W are like between 0 and 1. So here, like the numbers between 0 and 1. And so obviously when you like collapse it down to 2D, it's all going to be very much over top each other. And then we see here, these are like the Diagon era, as I call it, where you have all these Diagons for lots of values of sparsity.
Sorry to interrupt you again, Ben, just to clarify. So what you're saying is that in that fourth picture, there's a bunch of independent triangles in higher dimensions, which project down to 2 dimensions, look like they're all on top of each other, but it's
So these triangles are all like distinct. Yeah, thanks. You just can't tell because it's like, this is why I think the paper moves them all away like this, so you can see them. But then if you look at actual PCA, yeah, they'll be all overlapping, but the dot products are not intersecting. And you can see that more cleanly with the Diagons, where like each Diagon just connects to another one. And I've also tried to color code the dot products to be same as before. So like a blacker line means a much more non-zero dot product. So as you can see, the Diagons have very black lines because they're in just, you know, a one-dimensional subspace. And then as we move through the sparsity values, you get these pentagons that appear. And then there's some Diagons here, but they all just sort of like end up being vertical. So when they collapse down, it went very close to 0. And then we see
the label on these pictures is sparsity is 1 minus sparsity.
Oh,
correct?
Yes. I think I had, is there a note? Yeah, there it is. I forgot to add that. Yeah. So yeah, because I realized like yesterday, like last night when I looked at this, like, oh crap, I mislabeled these, but I don't want to go back to Python, and so I just put that down there.
Okay.
Yeah, thank you. So yeah, sparsity is 1 minus S. And so yeah, over here we see some more pentagons connected. Again, if you like could disentangle, if you actually like decided to follow each line independently, you would see that these are all disconnected pentagons. And then I've not included the lower sparsity values because it just becomes like a big soup, like a big blob of features. Okay, so why these shapes? As Daniel said, open problem. we don't really know. I like to think of, I think a reason, my understanding, which again, correct me if I'm wrong, but I think the reason the model likes these digons so much is because, say, if both features are sparse, so pick like a local digon, there's two features. If they both have sparsity, say 25%, then this subspace is a good spot for them both half the time. And then it's only bad when they both appear, which is like 6.25% of the time. So as the model sees it, it's like, this is a pretty good way of assigning features into dimensions, because and as the sparsity, this is if the sparsity is still kind of low, like 25%. As the sparsity gets even higher, like to 90%, then it still is good way more often than it's bad, because the goodness is adding them and the badness is multiplying the probabilities. And the paper also makes some connections to the Thomson problem from chemistry, which is just connecting the idea of, if you have like a sphere and you're trying to shove electrons into it and they're trying to get as far away from each other as possible, they also form into these nice polytopes. Again, I'm not sure how clean this connection is, or if it's just the pictures just look the same. But I don't think there's any mathematical argument to connect the problems just yet.
You're trying to keep the features as separate as possible. They're roughly the same, but they're different potentials. The mathematics that is any of them.
Yeah, different potentials. That's right. So something else I did was, you can actually solve the loss exactly if you ignore the bias. So if you're trying to shove two features into one dimension, so back to the digons, you can then compute the loss exactly as a contour graph. And that's another thing that I did. So now I think Liam or Jesse, sorry, I was sleeping, but did either of you mention first order phase transitions in either of your talks?
We did.
We did. Awesome. Because before, all the phase transitions were just like in quotation marks, but this is an actual phase transition. Or, phase change, or whatever the accepted nomenclature is. So if you like contour plot the loss with only two parameters, W1 and W2, you can, it's also worth mentioning, this loss plot is actually the exponential of the negative loss to make it more cleanly. If you actually try to plot this loss just by itself, it all looks like the same color, because it's all very flat. But at the sparsity value of, it's a really ugly radical, but it's roughly 0.417. You see that the model changes whether it likes these local minima or these local minima. So we actually see a first order phase change in the low dimensional biasless case for the model, which, yeah, I think is pretty cool.
What?
Ben will say more about this next week.
Yeah, and this Dan will say more about this next week. So ask Dan, Liam. Sorry, no, go ahead.
I was just going to ask what are the phases that we're looking at there, or should I wait?
No, Ben can answer. Yeah.
Yes, I can. Do you mean like what are the values of W1 and W2?
Yeah. What do they correspond to? What is the phase transition between? What are the phases?
Yeah, so these points, this is the constant importance case again. So I'm currently trying to, hopefully by next week, get my non-constant importance code to work, but it's being really annoying. So in here, we see that these values are one. I was going to have this up on my second screen, but my mouse literally just died this morning, so I can't get it, sorry. But these are like 1 on root 2, 1 on negative root 2. And these ones are like, from memory, I want to say 1 on root 2 times the square root of like 3 plus 5s divided by the square root of 1 plus 3s.
This is a mathematician answer. Ben, answer the question. What? Ben, nobody cares about the numbers, man. So
yeah, sorry. I'm just like thinking about what I think about when I do it. So yeah. What are the? So yeah, I think this low sparsity regime corresponds to it. Unfortunately, since the importance is constant, it will basically try to embed both features the whole time, because it's incentivized to do both. So this is not a phase transition in whether it embeds like one feature, the first feature, or the second feature. It's trying to embed both features the whole time. And then the transition is sort of in like what orientation it likes to put them in, I think. So whether it's like 1, -1, or just like both in the same direction. That's my understanding. I hope that
Right.
answers your question.
So the dot at roughly 1, 1 represents, so you've got two features being mapped to the real line.
Mhm.
And the phase at 1, 1, the local minima, corresponds to putting them both features pointing in the positive x direction, right? They're
Yep.
overlapping.
Yeah.
-1, the other phase, which is down the bottom left, is both of them pointing to the left. And
Yes.
the phases that are on the off diagonal, on the diagonal y = -x, those are embeddings that map the features into a diagon. So the upper left, bottom right are two digons. They're symmetric. So there's really only two phases here up to symmetry. There's
Yep.
the in the same direction phase and the digon phase. So this phase
Yep.
transition is the emergence of the digon.
Yep. I hope. Thank you. And then yeah, as this happens around sparsity 0.5, and then it'll just like get more and more strong as the and this is also a local maxima, obviously, in the middle. Okay, cool. So yeah, now just some quick asides on how we're doing for time. Just some quick things as well on how overtraining does this change. So here we've got a plot which shows the dimensionality of these features across training. So as we see, as the loss decreases, all of these features the model either decides we're not going to embed these ones, don't care, they can get set to 0, or we're going to put these ones into a half. The sparsity here is like roughly 30-40% from memory. I didn't write it down, sorry. And the features is roughly on the order of 100. And then what we see is to get a bit of a dip in the loss when it manages to shove another feature up into a diagon. It manages to put another feature into diagon. So this time, this is across training time over epochs. Another example, so I think Jesse showed this image in his first talk in alignment 1. So we could also ask the question of like, what if the features are correlated? Meaning, what if, say you've got 6 features and the first 3 are either all set to 0 together with probability S with a sparsity, or they're all sampled independently from the uniform distribution. So the model gets told during training, these features are always set to 0 together, or they're set to non-zero uniformly together. So if you have 6 features, 3 are correlated, and these 3 are correlated. I hope that makes sense about the correlation. Across training, initially they set the weights to be close to 0. And then as training continues, it takes the correlated features, so the ones that occur together, and pushes them away from each other. And then you get another phase change in the loss when these features then spread out. So I think here they put like limits on where they could go. Oh no, sorry, they didn't. Ignore that. And then finally, you get another little dip in the loss as they arrange themselves into this. What is this? Like a antipodal? Yeah, a bunch of antipodal pairs. What's a 6 vertice shape called again? Hexagon. Yeah, I'm not good with polytopes. But as you can see here, as the model forms these shapes, it lowers the loss, and as it like seems to sort of change between rough shapes, it gets a bit of a discontinuous dip in the loss. This is another plot that Dan made. I didn't ask if I could show this, sorry, but thank you. So we can see.
Quick, it's secret, hide it.
But you can see here that this is 5 features in 2 dimensions. So these ones never actually get to this is in the high sparsity limit. So sparsity is high. As you can see here over training, it eventually embeds 2 features, all constant importance, by the way. And then as these red dots are the snapshots in the loss, we can see that it embeds a 3rd feature and it gets a bit of a dip in the loss. And then when it embeds the 4th feature, it gets another dip in the loss. So yeah, these are some interesting, this one actually doesn't make sense to think about of time or training time as you move across, as the model manages to embed more features, it gets better performances in the loss. One little aside that I will leave us with before I finish is, so the Anthropic made this second paper where they looked at not just features for an infinite data set, as we saw before, but what if we had a finite data set? So what if the data set was like really, really small? Like what do features look like then? So for these plots I'm going to show you, I want you to think of sparsity being set to high sparsity limit. So as Dan said, this is much easier to, understand. Once again, features will be uniformly sampled between 0 and 1, but this time we're going to rescale the vectors to be radius 1 or norm 1. So if we have this matrix X, which keeps track of the features, and then also the training data that we have T. So as we increase T, we keep track of every single specific sample that we got. We can then think of these things I'm going to call hidden vectors, where we could plot the actual data that we sampled from. And now we see that it seems that the data points themselves for low data sets get mapped as polytopes and not the generalized features. So for an example, if the data set is tiny, like 3, then you see the features look a bit confused and the hidden vectors look nice and clean. And then as, again, T equals 30 is still pretty small, but you see as the data set gets larger, it maps the data set into polytopes and the features are not very well formed yet. And the loss we're using for this one, sorry, from Anthropic is a sum over the features and the sum or integral over each single feature. And then we divide by the data set T. So you can think of the features again as a column of W and these HIs as the data we drew from. And what we see is for low data sets, we get this sort of, if we plot the dimensionality again of the hidden vectors, like we plot the dimensionality of the features earlier, we get this interesting plot here. So we see the test loss in this low data set, it gets pretty good. And then as the data set gets larger, we then get this increase in the loss. And then as the data set gets even larger, we then get this decrease in loss again. And if you look at the dimensionality, it seems like the dimensionality of the hidden data is very high, low in the low data sets. And then as the data set gets larger, we see that the dimensionality of the features gets larger and the dimensionality of the hidden vectors get smaller. So we can see the features seem kind of confused here, and then we get nice polytopes for the hidden vectors and the data. And then as the and then in the middle, this is when the loss is the worst. We get this confused regime. And then once again, as expected, we get the features forming and the hidden data is a bit more blurred. And so this is the idea of like, is this maybe associated to the memorization phase with got low data set? And then as the data set increases, then it then generalizes, showing these high dimensionality of the features. Sorry, yeah, the dimensionality of the features then is what seems to be happening when you have the high data set or the generalization phase. So these are pretty like just interesting results, maybe associating what quantity to look at for the memorization versus generalization thing.
Can I ask a question, Ben?
Yep.
Is there any particular reason for drawing the middle regime there, like in terms of some particular ratio
like
or
this one, you mean?
Or just the whole band of it, I suppose. Like, is there any way to understand where that middle regime might theoretically be?
Theoretically, I do not know. I don't think so. It's basically they just define it as where the loss increases before it decreases again. So again, I think it's just experimental.
Also, it looks like hat-trick star on the bottom right. I couldn't help but notice that.
That's very true. Okay, so I think I think we are all sufficiently caught up, hopefully, on this paper now to be ready for Dan's talk and the second week. So key takeaways from today: Mech Interp is a area of study which takes these features and circuits and help what's going on inside the models. Superposition is one of the largest hurdles. I think a few of us here saw a talk by Neil Nanda where he said this was the biggest open problem that he would like to solve in mechanistic interpretability.
You said last hurdle. Nobody said last hurdle. First hurdle, maybe.
Largest hurdle. Sorry, largest. Sorry.
Oh,
Yes.
largest.
It is the largest. It is not the only hurdle. Yeah. And yeah, and the key takeaways is that as sparsity increases, features align themselves into more geometric, it's more happy to embed more features into more dimensions. And as it does this, it puts them into these geometric polytopes. And a promising tool for this would be, I got this from Anthropic, is that would be a good idea to be able to identify and enumerate or like sort of check over all possible features. So a great tool would be to maybe we could say in a network certain features, and because if in these like very large models, it can be very hard to see all features, but it might be nice to be able to see if certain features definitely don't exist and certain types of circuits don't exist, which would be good for alignment. And yeah, this is going to be a great testbed for playing around with all these SLT tools that we'll see later in the week and next week. I think that's where I'll leave it. Yep. Cool. Questions? Ask away.
While people in the chat are maybe typing their questions, are there any questions here? What about the modifications? You like that? Or sorry? The modifications.
Sorry, I got.
Or just the high sparsity limit?
Sorry, I didn't catch that. Was that a question for me?
Not really, no.
Okay. What would a resolution to the superposition problem look like? Yeah, that's a great question. I think somehow being able to, I'm just spitballing here, but I would guess maybe being able to somehow look at a neuron and being able to work out all the features that were somehow inside that neuron. Maybe someone else in the audience there has another answer for what they think resolving this problem would look like.
There's also more information than just which features are embedded in superposition, because some of them are arranged into geometric figures so that they're not all created equal, right? So
yeah.
Well, even at equal importance. No, I'm saying that like some of them get put into digons and some of them get put into triangles. So
yeah. How do things change? Yeah, so this actually, with the model they've given us, it actually doesn't work. I've tried this. Sorry, Alex. So if you instead have features being distributed over -1 to 1, so the model we have, the last step we do is activate with a ReLU, and so that just sets all negative values to 0. So yes, as Nathaniel says there, the ReLU is the problem here. So I played around a little.
I think Alex probably realizes that's the case, but it is a bit artificial. Like,
yeah, it is artificial
that we're using 0, 1. That is responsible for a lot of what's going on. So you could say that this model is a little contrived, but it is called a toy model after all, so that's okay.
Yeah. I did play around a little bit with trying to get it to work with negative values, but yeah, everything I did just made the polytopes go away. So I didn't play around with that long, but yeah, like Daniel said, definitely the model we're using helps a lot there.
Are you, or is anyone aware of work where we just explicitly break the symmetries that don't privilege any bases? Like in the residual stream, you could just, maybe cause different channels to erode at a faster rate or regularize them with a different strength.
You mean in order to encourage the network to use a basis that we're somehow prepared to understand? Isn't that pretty much along the lines of what Ben was saying at the beginning of the talk, which results inevitably in lower performance? Is that right?
But how much lower performance?
Yeah,
Right.
well, that's fair. Yeah.
Yeah, I guess, yeah, we don't know about that.
Seems like it's worth trying regardless.
Yeah, thanks. Could one takeaway of the superposition be that, in fact, looking at single neurons as are representing interpretable thing, not such a predictive perspective, and instead look at populations of neurons? For example, I think in neuroscience, like people are moving more in the direction of like, yeah, looking at population coding instead of like at some point you had people talking about the, I don't know, like marine Monson neuron or whatever. And then, yeah, it turns out to not be such a productive stance. And I don't know if like people in mechanistic interpretability or interpretability have been looking at a more like what happened if we try to understand the internal of the model via like a sort of like population coding hypothesis, population of neurons. Yeah.
Yeah, I definitely think that looking at individual neurons is, it's like still like, you know, if you even like think of like something like GPT, there's still like so many neurons to check. It's insane. I think.
What substance?
Yeah. And so I think, yeah, the issue, I guess, with looking at like overlooking at like multiple neurons is just like, again, the interpretability thing. So like, even if you like say you somehow understood like 90% of the network perfectly, but there's still like 10% you know what's going on there. Like from an alignment point of view, that 10% could still like try to kill you, I guess. So I suppose there's like this like problem of wanting to fully understand everything. So I guess that's where this idea comes from. But yeah, that could be a promising direction. I'm actually not super sure.
On that.
No, you go.
No, feel free to answer the chat questions first.
Yeah, I'll just deal with this one and come back to you. Yeah, I think this is something that answering the rotation thing, I think that's something that we tried, wasn't it, Daniel, at the start? I think the problem is if you rotate the features, you have to make sure that none of them are negative. And I think like acting with the features like an orthogonal matrix will make a lot of them negative, and then the model won't be able to recreate those ones, of course.
Now, the rotation question is asking something else. It's not actually in the toy models situation, if I understand correctly. It's about like across multiple different layers. You might, but I don't really understand the question. Isn't this question predicated on thinking that there's a privileged basis that you get to choose and then being unhappy that the network chooses something else? So I don't actually understand the question.
Yeah, I think
I don't think you know a principal definition of feature, do you? I don't.
No, I think I even asked the audience during that part of the talk. if that didn't give it away, I don't know what would.
Maybe a variant on that question is to both you, Ben and Dan. Is your intuition telling you that there might exist such a definition that makes things make sense, or that it's just like a silly question to ask in the first place, and it's always going to be too hard to define it?
A feature is whatever appears in a phase transition that puts something in superposition.
Mm-hmm.
Yeah, I think we're going to end up in a spot where it's like a tensor-like definition, where a feature is something that interprets as a feature or whatever. Like, I don't think we're going to end up with a super nice definition. But that's just maybe this is me being a bit pessimistic. Someone could just like rock up with the perfect interpretation one day.
Devin, could you expand on your question? Gives hope that this is a tractable road to go down. This meaning interpretability, mechanistic interpretability, presumably. Yeah, what do you say, Ben? What's the most compelling evidence?
So I would say, honestly, in my very limited time looking into mechanistic interpretability, given how young the field is, like it's what, like 2-3 years tops, like it's very new, and how few people work on it, how much progress has been made in that short amount of time by those few people, I think is incredibly impressive. If you asked me like 4 years ago when I first started learning about neural networks, would you think that image classifiers are interpretable? I'm like, oh no, it's all just a big soup of linear algebra, like it's all uninterpretable. And then they've made a lot of progress on this like image classifier. And then I would have probably said like, oh, but then, you know, token like transformers are very, very weird and like you wouldn't get those. And then they seem to have made some progress on identifying something in some smaller transformers. So yeah, I think it's still very early days. Like, I think if we compare this to any other field, like, I think the progress is pretty impressive so far. So I guess I'm optimistic. But I guess my actual answer is also, if this isn't possible, then I don't know, we could just sit on our hands and do nothing. But yeah, I guess.
There's just like a slight realistic counter to this, and that is that the vision circuit stuff is somewhat cherry picked, right? They're showing the neurons that are most interpretable, and there are a bunch left that we do not understand. And the same is true for the transformers. Maybe even these induction heads are kind of overhyped and don't, like, the explanation we have doesn't explain everything they seem to be doing. But yeah, let's stick with optimism.
Yeah.
Amen. Yeah.
Yeah, I guess when you like work in a field called mechanistic interpretability, you have to kind of assume that it's possible to interpret anything just by like the field's definition.
It's also the case that even if you think it's doomed, it could be a good bridge to wherever the good idea is that we need, right? Like you don't like, no mathematician makes progress on a hard problem by aiming at that problem from the beginning in some direct way. Like, I have a map, I'm going to follow the map. That's, nobody solves hard problems like that. You have to identify something in the rough direction that is non-trivial and interesting, and you take the first step, and then you'll adjust and take another step. So judging Mech Interp as a field on the basis of will this work and be the answer is like not, that's not the attitude of somebody who actually solves hard problems. Like, let's do this part and then we'll think about the next part, I think is the attitude.
Yeah, and that's just not how I think about like problems as like a mathematician. Is like, I like to think what's like easy toy stuff I can actually do math on. And then maybe I do that for long enough and something will pop up.
Another question. The term mechanistic interpretability.
Yep.
Are there other kinds of interpretability research, or like, is it all just mechanistic interpretability?
There's Bertology, I suppose. Yeah. No, I'm sure there's other. I'm actually not sure.
Yeah, maybe someone else here can take a stab.
Yeah.
What other kinds of interpretability?
Yeah, like,
yesterday we talked about like the probing being the maybe the more academic equivalent. So maybe the difference is mechanistic interpretability is really about reverse engineering. We want to understand the circuits, ultimately, how information changes within these models. And there are less ambitious aims, like just understanding some of the thoughts that the model has, some of the features that get activated, and finding correlates of thinking, not necessarily how they transform, but just that, I don't know, Rome and Eiffel Tower were active in this model at this moment.
so just on that point, are there alternative? Are there any other subfields that are X interpretability, if that makes sense? Just like,
There's a developmental interpretability.
Yeah, that's a very young field.
Minus 3 days old. Okay,
Cool.
I think we can probably wrap it up. Thanks
Awesome.
very much, Ben.
Thank you. See you guys in person in a few days.